the analyses that we can look at in a forest plot or a meta-analysis. So I'm where I usually am. I'm in RevMan in the Data Analyses tab. I've gone down here into my comparison and I'm looking at all the data. What I'm going to do is I'm going to put my mouse on the all data and I'm going to double click, which is going to open up this interface that I have. So we're familiar with what is in this section, the tables and how that data works. And we discussed last time what this forest plot is representing. But now what I want to do is talk about some of the analyses that we can do on this data set. So the first thing I want to talk about is what we have down the bottom of this table. And to do that, I'm going to have to shrink the prevalence table so that it will show up. I'm just going to shrink the forest plot. So let's think about what we're doing when we're doing a meta-analysis. A meta-analysis is an observational study of studies. So in our analysis, each study is an observation. Now in primary research, each animal or each farm is an observation. But now we have a study where the unit of concern is the study result. So I have one row of data and here's the row of data from that study. I have another row of data and here's the data from that study. And so I get a summary effect for each study. I'm actually, by the way, going to change this over to the odds ratio just because the data are a little bit more interesting. I'm not saying they're the right data for this example, but they're more interesting. Now, so this means that what we have, let's imagine that all of these are from the same diagnostic test. What we have here is 17 estimates which, based on our analysis, our interpretation of those studies, are at the very least relevant. So when we did the PICO format, we identified studies that would be relevant to the question of whether cattle and buffalo had a different seroprevalence. At the moment, I'm not going to talk about the assessment of quality, but basically the assumption is because these studies passed the screening that they are at least relevant to the question. So now we have 17 different estimates of the difference in the prevalence of brucellosis in cattle versus buffalo. Actually, we're going to express it here as the odds. Is the odds of being seropositive for brucellosis in cattle compared to being seronegative, is that different to the odds of being seropositive in buffalo versus being seronegative? But what we'd probably like to do is combine all those data and see if we could come up what's called a summary effect measure. So each one of these is an effect size, and what we'd like to do is come up with a summary effect measure. But before we do that, we have to make the assumption or evaluate whether the idea that all the studies are actually being drawn from the same population is valid. Because there may be clinical or methodological sources of heterogeneity in these 17 studies, which means that they're actually not estimating the same thing. So let me just give you a very basic example. Let's imagine that the first studies from 1 through to 17, this first group of studies, let's just imagine for some reason that they had only studied females, whereas 2 through to 9 had only studied males. I know that's a made-up example, but let's just imagine that's what happened. In that case, if sex is associated with seroprevalence, then the estimate may be different between those two subgroups. Males may have different to females. Another example that's quite common is if we have beef cattle versus dairy cattle. So what we need to do is first test the assumption about whether there is homogeneity of the effect. So does the effect of cattle versus buffalo look to be the same in each study? Now, we can do this as a couple of ways. First of all, we can look at the estimates. And what we're seeing is that there are lots of estimates that seem to be near 1. There's a few that are protective. There are some that's showing a much higher prevalence in cattle. This one is showing a much higher prevalence in cattle. Now let's go over and have a look at the forest plot. I'm going to change. So what we can see here is we have one estimate that shows that's more prevalent in buffalo, a fair few estimates that are showing that there's no difference, and then we've got a couple of studies suggesting that seroprevalence is more common in cattle. So there's really not much homogeneity. Homogeneity, it seems like we actually have quite a lot of heterogeneity. We're getting different associations from different studies. Now this concept is very much like the Breslow and Day chi-squared test for homogeneity, which you would have done in your basic epi class when you were doing effect modification, because it's very much like the idea of effect modification. What we're asking is the effect, does it appear that the effect is the same in all the studies? This is exactly the same as when you looked for effect modification or interaction, and in your Mantel-Hansel you stratified, and what you would have done is you would have looked at the Breslow and Day chi-square test for homogeneity, and you would have, the null hypothesis was that the estimate was the same, and you would have rejected the null hypothesis when the p-value was less than 0.05, and you would have reached the conclusion that actually we should reject the null hypothesis and conclude that the strata are different and that there is effect modification, so that third stratification variable was associated with a change in the exposure-disease relationship. That's what happens when you're doing the Breslow and Day chi-squared test for interaction. Well, this is a very, very similar concept. We are also doing a chi-square test, and it is asking the question about homogeneity. The assumption is that they are the same, and we are going to reject that assumption when this p-value is less than 0.05. Now, what you see here is that we have strong evidence that all of these trials are not estimating the same thing. So we must have, it appears that we have heterogeneity. We also have the I-squared, which is another measure of heterogeneity. An I-squared of above 70 suggests that there is substantial heterogeneity.